Okay, good afternoon, everybody, and welcome to another Friday lab version of MI212. This afternoon, we're going to go through the problem from the previous lecture for Advanced PKPD Topics 3 for multi-scale multiple endpoint modeling. Start off today, if there's any questions from the lecture, please post those to the question forum. Otherwise, we'll get going here. I'll just go through the problem statement, and if there are any questions from the lecture, I'll stop and try to address those before we get into the actual solution, at least the one I've posed for this problem. So again, just going through the sort of hypothetical problem that I've set up here, dealing with inhibition, in this case, of cholesterol ester transfer protein, CETP. A reminder that CETP works as a essentially a transfer enzyme of cholesterol ester and triglycerides between the lipoproteins. It's shown here transferring them between LDLs and HDLs, but the fact of the matter is it's involved in transferring in and amongst LDLs and in and amongst HDLs as well. And that's really how these HDLs become different versions of themselves as they transform through sort of through this cartoon here. And I realize I may have a typo here. This is actually, I think, triglyceride rich, because as these HDL particles move from HDL3 to HDL2 and then toward the liver for clearance, they become more rich in triglycerides, and they end up giving their cholesterol esters back to the LDLs. And so these LDLs build up the cholesterol, so they take it back away from the HDL and they build it back, and they ends up causing a lot of the oxidative damage that we see with things like cardiovascular disease. Now you can imagine that, historically, I guess, if you will, in the evolution of biology, this was probably a useful process in times when foods and such weren't as readily available as they are today, and you needed to keep the cholesterol that you had in circulation. And so as it was going to be destroyed by the liver, this process would take it back and say, well, wait a second, we need some more, because we actually do need cholesterol for some cellular functions. However, now we're trying to kind of block that process so that we block the return of the cholesterol back into the system and facilitate its return back to the liver to get chewed up. And so, in fact, what happens is that these triglyceride, I'll need to change this, the triglyceride HDLs are cleared more quickly. And so by blocking the formation of these HDL2s from 3s, we end up then elevating the entire pool of HDL cholesterols. And then the reverse happens in the case of LDLs, and that's why with CETP inhibition, you get a lowering of LDL cholesterol in total. And so the sort of hypothetical situation I've set up here, again, I've taken this, there are two publications that show results from CETP inhibitors along the lines of PK and PD that we're using for this example. And so I've taken pseudo versions of those and come up with parameters that I thought would simulate out something near the actual observations. And we're using that for this hypothetical example. So we've got a study where we've studied 12.5, 25, and 50 milligrams. And actually, if you look at the data set, the study must have continued on from there. And so we also have 100 and 200 milligram data within that, that data set as well. Subjects were dosed for 14 days, once daily. And then we have the PK and PD measured through day 19. The twist to all this is that the concentrations that we're measuring for the drug actually represent total drug. It's the way that the assays run. You pull out the plasma and you measure the total amount of drug in that plasma, which represents both a bound and the free fraction. And this is represented in the data set as compartment 2. Our PD measurements, we have the receptor itself, the transfer protein CETP, and again, that's measured as a total concentration in the plasma. The plasma is drawn, and the amount of CETP that's in there isn't differentiated between its free or its bound form. And so that value represents compartment 5 in the data set. We have an ex vivo assay that determines the activity of the CETP or the free CETP that does remain in the plasma. And this is actually expressed as a percent of activity relative to baseline. So in other words, it's a CETP inhibition value. That was in the data set as compartment 4. The total HDL cholesterol in the serum is in the data set as compartment 6. And I do apologize, I've added this since the last lecture. We need the molecular weights here. If you recall from the TMDD, target mediated drug disposition work, when you start to deal with binding kinetics between drug and receptor, you need to make sure that you're in molar units so that you can account for the appropriate one-to-one binding. If you look at the actual data, you'll see that these total CETP concentrations go up over time. If you recall back from the target-mediated drug disposition lecture, that's very common. If your complex clears more slowly than your free CETP. And if you look at the inhibition data, and I do apologize, I looked back at the simulations. I think what happened here was I simulated with too much variability, so it's actually hard to see this, but it was intended that there was a bit of apparent tolerance occurring where if you looked at the CETP inhibition versus drug concentration, it appeared to be shifted out on day 14 compared to day 1. But regardless of that, the idea was that you'd use the TMDD model to help express your model to describe CETP inhibition, and then you would use that to then carry forward into an HDL model, and in a sense use a bit of a transit compartment model there, although we have to assume some initial conditions for that, and then predict out the HDL changes. Again, making that assumption that one form is cleared more quickly than the other. We looked through the data last time just to show the way that it's structured as far as the different observed values within the different compartments. I won't go through that again, but that's the way the data are set up. Now, I've added this, and again, I'll post this this update along with that one fix, just to show you the actual observed data here. If you haven't gone ahead and plotted this yet yourself, we have the observed total drug concentrations here. You can see there's the sort of typical profile. This is day 1 dosing. We have troughs taken for the next several days, and then on day 14 there's another full profile taken. CETP goes up to near 100% at the higher dose groups. We get troughs, and actually you can see here that those troughs are slowly dropping over time. Again, that's representing that's representing some potential tolerance occurring within the model over time, just a slight bit. And then you can see on day 14, again, with the full profile, the way this is set up is that at every concentration time, there was an inhibition assay run as well. But again, you're nearing up near 100% inhibition with the higher dose groups. This shows that total CETP, so this is the plasma concentration of the receptor, CETP, both the free and the bound concentrations that's going up. Again, that's representative of a case where your complex is being cleared more slowly than your free CETP, so the total value goes up over time. And then finally, that translates into an HDL-C here that increases over time. Now, you recall we had dosing for 14 days, and then we actually followed out for 5 days afterwards, and we're getting back down toward baseline. Similarly, you see the elevation in HDL cholesterol, and then over that next 5 days, that slowly begins to return to baseline as well. So at least we have some of that follow-up data within the data set. So I've also added this to kind of help visualize how I see tackling this problem. And other ideas are certainly welcome, but this was sort of the intent for why I chose this example. I thought it would be a good choice to help highlight not only the material from this lecture, but the past lectures. So we have here the PK, or the target mediated drug disposition model. And what I'd hope to do too is highlight how you can use some of this information, not just for the PK, but also to help drive the pharmacodynamic relationship, in this case for CETP inhibition, and then how that feeds into the PD. So just walking through this schematic, we have our free drug, we have our free target, and then we have the complex of drug and target here. Now, if you recall, when we're talking about total drug and total receptor, in this case CETP concentration, one of the first things we need to do is make sure that we're in molar units. And then the total drug is represented by the free plus the bound, and the total CETP is also represented by the free plus the bound. And these are the two quantities in this situation that were actually measured and reported. Now, the other point, and again, hopefully the schematic helps to bring this out a little more, is that you can imagine that the activity or the ability of this CETP to transfer triglycerides and cholesterol esters back and forth is really a function of the amount of free CETP that's around. And so as you bind CETP up, this free is going to decrease, and so therefore your CETP activity will also decrease. And so you can think of the activity at any time t is equal to the concentration of CETP that's free divided by the amount of CETP that was there at baseline. And so the inhibition is actually expressed as a percent, is actually just 1 minus that and then multiplied by 100 to make it a percent form. And so as this free value goes down to near 0, then you're going to have 100% inhibition. As the free returns to a value near or at the baseline, then the CETP inhibition ends up going to 0. So that's the relationship that I envision there to help fit those data. And then getting down to the HDL cholesterol, again, we have, if you can think of this as the HDL3s and the HDL2s from that prior schematic back up here. So we're really just kind of taking a box and throwing it around the 3s and the 2s here. So again, this is in a sense, it's kind of like the transit models that we were looking at before, where our total HDL cholesterol that's measured is actually the addition of the cholesterol ester rich particles and the cholesterol within the triglyceride rich lipoproteins. And there's a transfer rate called here KHDL on that's affected by the amount of free CETP. And so the difference here is that we actually have removal rates from each of these compartments. And so this leads a bit to some identifiability issues that we have to make some assumptions on within the model itself. But again, the theory here is that these triglyceride-rich molecules are cleared more quickly than the cholesterol ester-rich molecules, and so when you block this off, you block the sort of the faster route of getting rid of HDL cholesterol, and so you get a buildup within the cholesterol ester-rich side of things because this value is smaller than this value, and so you get an increase in the overall amount of HDL cholesterol. So that's the sort of the theory behind the model. I do see we got a couple of questions posted here. So before we get into the code that describes this system, we'll let me take a look here for a minute at the questions. Yeah, so the final question here while I'm on this slide is that, yeah, that final bullet should read that these triglyceride-rich particles are cleared more quickly than the cholesterol ester. So I'll fix that, and the next posting of the notes will have that fix in it, as well as these schematics to help you on your any references back to this material in the future. The other question comes up on back into the lecture material here. Let me just find it. Page 124. Okay, so the question is on page 124, what part of the model demonstrates incorporates bone metabolism rebound? Okay. And actually that ties in with I'll kind of read the next question and hopefully answer these all together. Next question is, how does equation 7.1 fit into the overall model? So this is equation 7.1 right here, and so this is the equation that is describing the lumbar spine BMD longitudinal changes. And the way that this particular equation works is that the input rate, or the amount of bone formation, is driven by the activity of osteoblasts. The marker for that activity is bone-specific alkaline phosphatase, BSAP. And the amount of bone that is resorbed or chewed up is a function of osteoclast activity. The marker for osteoclast activity in this case is the serum C telepeptide, or CTX. So these bone markers are what's described within the broader model. Let me just go back up. I'll just grab the schematic here. Where when we talk about the osteoclast and the osteoblast, we're actually talking about their activity within the model. So the differential equations that describe osteoblasts and osteoclasts are actually describing the activity of those particular bone cells as measured by those bone formation and bone resorption markers. So the, if you will, DOB-DT is actually DBSAP-DT, and the DOC-DT is actually DCTX-DT. They're one and the same. So the way then that the BMD is drawn from this, again, is just a function of how these osteoclasts and these osteoblasts change over time. The way that rebound occurs within this model is most notably and probably most easily explained by TGF-beta. So we have here a really a kind of a good example, I think, of a precursor pool model where latent TGF-beta is more or less stored within the bone, and then as osteoclasts resorb bone or chew it up, part of that activity actually releases and activates the active form of TGF-beta. And so here you've got this stimulation inhibition function for osteoclasts, which if you recall from the precursor pool models, whenever you do that, then you get a buildup of this latent TGF-beta, and that leads to a lot of the sort of rebound effects, because then TGF-beta goes in and feeds into to affect the differentiation and the formation of responding osteoblasts into osteoblasts, as well as osteoclast precursors into osteoclasts. So that's probably the simplest way to describe how that rebound is built into the model, going back to the core theory of our precursor pool models. And then we give an example of that actually down in this figure on page 126, where we're showing that slow buildup of latent TGF-beta over time for each of these treatments. And really that corresponds to the tolerance development, if you will, of the active TGF-beta. And if you kind of follow the slopes of these, they correspond to sort of the tolerance that develops over time in the bone resorption and formation markers. So hopefully that wasn't too quick of an explanation for how that tolerance and rebound is sort of inherent within the model, and then that all links into the BMD changes. Okay, so getting back to the problem for this week. Let me come down here and get into SIMI. So one note about the model right now, I started to rerun it this morning at, well, this is actually, I think, 10:30 our time, 9:39 at the time where the server is located. And it's still going. So I ended up just running a max eval 0 on this, just so that we had something to look at in the class. So I'll post everything up, but know that it's going to take a while. And if you run it on SIMI, again, if you don't keep your session open, it will close and the NONMEM run will stop running. So if you're going to run this particular example and you have a local setup, you may want to try it locally, or leave yourself plenty of time to be able to stay in the session on SIMI. Or just run it with fewer evaluations just for your own examples. That said, we'll take a look at the control stream. bigger. Okay, so the first thing that I did in here, again, trying to keep things as straightforward as we can, but not missing an opportunity to show you where you could use these things. I actually had the L2 data item within this data set. Because a lot of the PK and PD measurements were taken at corresponding times. For example, the PK and the CETP inhibition were always taken at the same time. And then the HDL cholesterol and the plasma concentrations of CETP were also not taken as frequently, but when they were taken at the same time as PK. And so within the data set is an L2 data item to allow for accounting of that. I was trying to speed things up with the fitting process here, and I just dropped that for now. But it may be something that you would want to consider if this was a real life example. The data file I had posted up earlier this week. And then the model structure itself, I kind of gave you a good lead into this by telling you what compartment each of the endpoints were put into. So we've got our dose going into the gut compartment, PK in a central compartment, which is our default observation compartment, peripheral. So we're setting this up so that we can have a two-compartment PK model. Our CETP compartment, and this is actually where the inhibition data are. The complex is in compartment 5, and then we have the cholesterol ester and triglyceride-rich HDL moieties in compartment 6 and 7. The PK is pretty straightforward, our typical kind of PK parameterization. Another thing that I did not do on this is go full out on inter-individual variances. In this case, they're just on clearance and central volume. Again, depending on your data, you may want to explore covariates, etc., and additional inter-individual variability. We have the scale factor here so that we can go from the milligram dose to the microgram per liter concentrations, elimination rate, and we've got our intercompartmental transfer rates. If you're interested, there's some code here that gets you the alpha and beta half-lives, and those can be tabled out. And then here's where we get into the target-mediated stuff, and this is very straightforward as compared to the lecture notes. In fact, I probably grabbed some of the initial code from the lecture notes. So we've got a baseline concentration for the free target, in this case CETP, an internalization rate for CETP, that's actually for the complex, a degradation rate for the free CETP. One thing that I'm not sure if the lecture notes were written this way, but I actually wrote it as the KD, which is the dissociation constant. The reason I do this is that this is often what's thought of as the EC50 when we're looking at just like inhibition versus concentration data. So we can go back and look at where this value falls compared to what our expected EC50 value was. And then K on and K off are typically how we look at this, but the the ratio of K off over K on is KD. So in this case, we actually just flip things around a little bit, but that's just algebra. And then the synthesis rate for CETP we set equal to the base value times the degradation quantity. And again, this is just using the steady state initial conditions, assuming the the integral 0 at time 0 to solve for that. I'm going to pause just a second here to read some questions. Question, would the drug concentration in the HDL be assayed from the same blood draw? In a sense, yes, they'd probably be drawn during the same blood draw. You would probably have two separate tubes. One may be for plasma, one may be for serum. And then they'd split off and typically go in different directions, one to the PK assay lab, one to the central lab. But the point there is that they're generally drawn at the same sort of phlebotomy sitting, same site, and more or less at the same time. So, the L2 captures correlation there, and so you can imagine that as a simple example, if somebody wrote down that they took the sample at 8 o'clock, but both the actual draw started at 10 past 8, that 10-minute error would be included and so therefore correlated and captured by the L2 for both the PK and the PD measures. So that's the point to that. And by the next question is the ex vivo test. So the same notion, the ex vivo, depending on how it needed to be collected, it very likely would again be drawn at the same time, perhaps a separate tube depending on what needed to be drawn in that case. Okay, so getting into the HDL cholesterol parameters, this is where it gets a little more original, I guess. And again, this is sort of my take on how I could imagine it. It's not necessarily the absolute correct way of modeling CETP inhibitors. It's just again something that based on what I saw in the literature would make sense. So the baseline value, so you start off with where that population and that then expanding it with inter-individual variability, where the individual would start from. Now let me just jump back here to the schematic. So there's amount of cholesterol that's here in the CE rich, and there's an amount that's here in triglyceride rich. And if you recall, the one of the assumptions that we usually make during a transit compartment model, because there's no sort of leaking of any of the transit until they get all the way through, you assume that the amount here is equal to the amount here, and then if you had a third compartment, it would be out here as well. In this case, we're not going to make that assumption because there's different clearance rates here. You can imagine that there could be different amounts in each of these sort of subcompartments, if you will, and so we've got a parameterization that helps to account for that. Back here, there's this HDL CE fraction. That's my parameter name here. So this is the fraction of HDL cholesterol that's in that CE rich pool. And again, I think we had shown this a couple weeks ago, we use this logit, which constrains that fraction to between 0 and 1. And then the amount that is the amount of cholesterol that's in the triglyceride rich is simply the base value times 1 minus that fraction. The amount that's in that cholesterol ester rich compartment at baseline is the base value times that fraction. And so the sum of these two again equal the total HDLC at baseline. And those are fed in, just to show you down here, to initialize compartments for 6 and 7, respectively. And then 4 is the amount of free CETP, and at baseline, or the initial value for that is base, which again from the target mediated stuff is defined up here as theta 6. So then we have removal rates for HDL cholesterol, the cholesterol ester-rich particles, the triglyceride-rich particles, and then this is where it gets a little bit interesting, and you got to go through and just solve out the algebra here so that you're safe at steady state and you don't get parameterization or identifiability issues. We actually go on and solve for the KHDL on, which is, KHDL on. So we're actually solving for this value based on the other values and the initial conditions. And we're also solving for the synthesis rate for HDL as a function of, again, the removal rate for these cholesterol-rich, ester-rich particles based on the transfer to triglyceride-rich and the initial condition for this particular transit compartment. So again, those are sort of requirements, if you will, unless you had, I could imagine actually, I do believe they do have assays where they start to fractionate out these different subparticles. I guess in that case, if you actually had observations within these different fractions, you then could better identify the system, and you wouldn't have to sort of make those initial condition assumptions. Okay, and we looked here at the initialization. I've also defined in here the molecular weight for the drug and the molecular weight for CETP. Again, those are required when we get down into the differentials because we have to eventually convert everything from the reported units in milligrams and micrograms, etc., down into nanomolar or some other equivalent molar concentrations for the drug and the receptor, and that's done down here in the DES block. Now I put in a day code here. That's just for myself. I use that later on in some of the plotting. So I'm going to make this a little bit smaller just so it doesn't wrap all the way around on me here. Okay, so I made that smaller. If that's too small, if somebody could just quickly type in a question, too small, I'll ramp it back up. But some of these lines are fairly long. I don't want them to spill over. And so the first few lines of this are, again, taken more or less directly from the target-mediated drug disposition lecture. So you've got a depot compartment, you've got your central compartment, your peripheral compartment, and within that central compartment you have equations describing the on rate and the off rate of the complex and of drug to complex and drug back from complex, and then the transfer to and from that peripheral compartment. and again, we start to set things up here in nanomolar concentrations as well, because then when we go down and start to describe, again, the binding between the free and the free and the complex CETP, we switch into nanomolar units. And so this is the synthesis rate of CETP, the degradation rate of CETP, and then when drug is around, you get, again, this on rate to the formation of the complex, and then the dissociation from the complex as well. This DADT5 describes the complex itself. So I guess just to think about this when we're talking again about the CETP that's measured in this particular example, we're talking about total CETP, and so that's going to be the amount in 4 plus the amount in 5. When we talk about drug, we're talking about total drug, and so that's going to be the amount in 2 plus the amount in 5. So just when we go down into actually figuring out what the observations are, you need to think about the fact that we're going to have to add this plus this, and then actually back convert it out of nanomolars and into the reported concentration units. Likewise for CETP, we're going to have to add 4 and 5 together, and also take it out of molar quantities and back into the reported concentration units. Likewise, you could take the reported concentration units for both of these and just table them within the NONMEM file as nanomolar values as well. That's actually probably the easier way to do it. But if different members of the team, I guess, are used to seeing the sort of the microgram per mil type concentration units, it may be easier to parameterize it this way and just make sure you keep things straight within your code rather than trying to introduce new values. Compartments 6 and 7 are the two sort of sub-units or sub-moieties of HDL cholesterol. So we've got the CE-rich in 6 and the triglyceride-rich in 7. And again, so we've got a synthesis rate of the HDL cholesterol being formed first as the cholesterol ester-rich moiety. It has a removal rate, so that sort of down arrow from the schematic. And then it also can be converted into the triglyceride rich. And so here's the trick here, is that process of being converted from 6 into 7 is being driven here as a function of the amount of free CETP that's available. So when there's no effective drug and the A4 is equal to CETP at baseline, then everything continues on as its own steady state condition. In other words, it doesn't change. As soon as you decrease the amount of free CETP, this fraction here goes down below 1, and so you begin to decrease the transfer rate from 6 to 7, and so drug is therefore reliant more on this process, or I'm sorry, cholesterol is in HDL is more reliant on the removal of HDL cholesterol ester rich, which again is slower than if it carried through this process, went into 7 and was removed by KHDL-TG. And so again, you see a buildup of A6, and actually you end up seeing a decrease in A7, but the buildup in 6 becomes greater than the decrease in 7. And so your sum of 6 and 7 goes above the baseline sum of those two. Okay, so the error blocks next. I see another couple of questions, and so I'm going to jump into those while I have a second here, and then we'll get into how you actually translate these differentials into the observations. So the question is, given the data set, are the target turnover parameters K on and K off identifiable? In this case, I believe they are, because we have observations of the, I think it actually helps that you have observations of the total PK and the total binding, and then you also have, in an indirect way, we have a measurement of the free because we know what its relative amount is relative to baseline by that inhibition function. And so, I guess in thinking about it, we actually have measurements of total drug concentration. We have a measurement of total receptor and complex, in this case, the bound and free CETP. And then again, we have, through that inhibition, in a sense, we have a measure of free CETP as well. And so that allows for I think the full identification of that TMDD model, which is actually fairly rare to be able to do that because it often is over-parameterized. Okay, question here. You seem to be saying that HDL cholesterol ester complexes with CETP. So are there really two TMDD components, HDL and CETP, and drug and CETP? In a sense, yeah. You could imagine that, although it gets to a point where the relative quantity of HDL relative to CETP, there's a lot more HDL out there, and so the HDL values aren't, the total HDL aren't themselves affected by CETP. And so the disposition of HDL isn't affected by CETP, and so you don't really have to consider that within the model. Certainly if it built up to larger quantities, you may need to. But you can make some assumptions there that it's insignificant relative to the total amount of HDL. But yeah, that's actually kind of a good point, and something that you would want to think about it. And in fact, my understanding is that the complex isn't that there's two separate complexes. It's actually the fact that you've got I guess you think of it as two complexes. So the drug and the CETP, and the CETP and the HDL. But that complex between CETP and HDL is not something that affects the disposition of either directly, and so you don't need to really account for that within this particular model. But intuitive thinking, though, that's good. Okay, so back to the error block. So we had mentioned up here there's a whole mess of things going on, because we've got a differential that we normally think of as A2 describing the free drug concentration. That's usually what we're measuring, but in fact, in this case, we're measuring a total. So the first thing that we need to think about, and the way that it's parameterized, is that this free concentration up here is still being described within this differential in microgram quantities for the mass transfer. So the first thing we need to do, if we want to add it together with the amount of drug that's in this complex, where this complex is within this particular parameterization of differentials being described in nanomolar quantities, is to convert the free drug into nanomolar quantities, and so that's what this line's doing. We can then add together this free drug plus the amount that's in this complex, and that is our measure in nanomolar quantities of the total drug, so the actual amount that's being assayed. But the truth is that we're not asked, the assay didn't report us quantities of nanomolars, it's reported micrograms per ml, so we can back transform to microgram per ml quantities. You know, you could have done this the other way too. I could have flipped around A5 from nanomolar and then added that to A2. So again, it's just algebra, but you got to make sure you end up with the right units in the end. The CETP inhibition, I had mentioned before that really all this is sort of 1 minus the activity, if you will, and that activity is the activity relative to baseline. So it's the amount of free CETP divided by the amount of CETP that was there free at baseline, and then we just make it a percent. So it's really 100 times 1 minus that fraction. The total CETP, similar to how we did the drug concentration, is the amount in 4 plus 5. These are both parameterized as nanomolar, so we can just add those together. But then the reported concentrations are actually micrograms per ml. And so we have to do the appropriate back conversion here, similar to how we did it with the drug concentrations up here to get us back into the units that we observed. The final piece for this, and we talked about this, is that the total HDL cholesterol is actually just the sum of 6 and 7. So we add those together here. If you wanted to plot out that change as a percent, we've provided the expression here. And so then this gets back to the data set structure. So the DVs that are in the data set for compartment 2 are actually not A2, but it's actually the total drug. And so we say if compartment equals 2, then IPRED is total drug. Again, it's not A2, as we would do in a lot of cases. The inhibition is this expression we derived up here. Total target is total CETP. Again, that's this piece here. And then in compartment 6, again, this is where this isn't the amount in 6, because A6 is actually just the the cholesterol ester rich HDL cholesterol. Here it's actually we're telling it it's the sum of 6 and 7. And then set this up so that we can have combination error structure. Now, one thing to note here is how I set this up. A lot of times we'll do, within compartment 2 of error 1 plus error 2, 3 plus 4, 5 plus 6, and then 7 plus 8. But I've actually set this up so that if you wanted to do and use the L2 data item, when you use that, you aren't necessarily correlating the proportional and the additive parts. You're correlating the proportional from one measure to the other and the additive from one measure to the other. And so in order to set that up right, you have to sort of order it in this fashion. I think you guys have probably learned that either earlier in this course or in an earlier one of these training sessions. The rest of this, I think, is pretty straightforward. We have our theta block. Set things up here for omegas. Didn't set up a full block in this case, but you could certainly consider that. And then I've included in here, again, although we didn't run it that way, how you would set up the sigma block if you were using the L2. So again, you have that as reference. Instead, we use just the more typical sigma block here. So that's the model itself. And running out of time here. There are a couple more questions. I'll have to post the answer to those back up to the forum. Apologies for not getting to all those in time. I just want to show some quick diagnostics from this model. Okay, so when I post up the answer, there'll be something called analyze.r, which is the R script that does some very basic plotting for this particular example. So we're reading in the data set, we're stacking it as we've done before. Make that a little bit bigger here. We're stacking it so that we can plot things simultaneously. And then I've also gone ahead and I've included these compartment labels so that rather than when we plot by compartment, we have something that's more readable than 2, 4, 5, and 6. And looking at the concentration, in this case, each of the PK and PD values versus time. This should, you can tell I copied code from the last lecture. This should actually be just DV here. But we can go back and we can look at how well the fit was to the inhibition data. So just kind of keying in on one individual here, we can look at the how well we fit versus the observed inhibition data, the change in HDL cholesterol, the change in total CETP, and again here you can see that rebound, or I'm sorry, the return to baseline occurring for CETP. You know, one thing that could be criticized about this is that you didn't get all the way back down to baseline and back up again. And so you don't know if you're truly observing any rebound phenomena. So that might be something you want to feed back to the team is, hey, can I get data for a little further out next time? And then also you're fitting the PK here as well. And then there's also some plots within that script that show the inhibition versus concentration. Those are pretty straightforward. Again, there's a little bit more variability within those plots than if I were to re-simulate things. I'd put less variability in there. I think there's more in there than actually occurs in reality, and so that the some of the signals aren't as clear as I hoped they would have been. But a couple of quick points here. I do see a question about getting a PDF of the exam questions. I will pass that along to Joe to see if that's something he can provide. Also a reminder about the exam that was posted up today, and it will remain open until just before class next Friday. So 2 o'clock next Friday. That site will close down, and then I'll come in and go through the questions with you on that. Bill Knable is going to be teaching the lecture next week, and then we'll follow on from me after the review of the question to go through the lab section of next week's lecture. And I think that does it. I think I've gotten through most of the questions here. There are a couple that are tailing, and again, I'll just follow up on the forum for that. The one just came in, where did you post the solution to the problem from last week? I believe I put it within last week's lecture material. It should actually, let me see if we can get there right now. Well, It should be right under the last week's lecture information. Should say something like Chapter 6 problem, or I forget exactly how I titled it, but I think it was pretty straightforward as to what it was. So it should be right on the MI212 main site. All right, well, thank you, everybody. I do encourage everyone to, again, continue to look through this problem. If you have any questions, you can post them to the forum. And good luck with the exam and the questions on there. Again, hopefully they're pretty straightforward from the notes and the lecture for the last 2 weeks. And we will review those next Friday. Have a great weekend, everyone. Take care.